So there's our m of ty. There's our n of ty. And so we know that what we need to do is, we already know this is not an exact ODE. So since it's not an exact ODE, we're going to find this integrating factor mu. And d mu dt is m sub y minus n sub t over n. M sub y minus n sub t over n. So we'll say not exact, find mu, and try again. All right, so this is times mu right here. So obviously what I need is m sub y, n sub t, and n. So m sub y is going to be the derivative of m with respect to y. So the derivative of 3ty will be 3t, and the derivative of y squared will be 2y. We've already calculated these, in fact, so we don't need to do it again. N sub t, we said that that was going to be 2t plus y. And that should be exactly what we came up with up here. 2t plus y. All right. So we're close. This is not a long process after this. Now I can just plug in what I have. So m sub y is 3t plus 2y. N minus n sub t is 2t plus y, all divided by n, which is t squared plus ty, multiplied by mu. Now we can do some reduction here on top. 3t minus 2t is t. 2y minus y is y, all over t squared plus ty. Wait a minute. This looks like I might be able to cancel something out. Well, if I factor out a t here, I notice that if I factor out a t from that denominator, then I'll have t plus y on top, t times t plus y on the bottom. And so this and this cancel out, and I'm just left with, what were we solving for? Well, we were looking at d mu dt equals 1 over t times mu. And see, that's a separable differential equation. So what we would do with separable differential equations is divide the mu over 1 over mu times d mu dt. And the reason we're doing that is because when we integrate with respect to t, that'll change our variable of integration to mu on the left-hand side. So integrate here with respect to t, integrate here with respect to t, and we get the integral of 1 over mu is the natural log of mu. The integral of 1 over t is the natural log of t plus some arbitrary constant. But wait a minute, with the integrating factors, we don't need the constant. You could put it there, but you're just going to be doing a lot more work when, in the end, the arbitrary constants are going to combine. Remember, this is just a factor to make it all work out. So there's more than one possibility for that factor. And so if you exponentiate both sides, you just get mu equals t. Great. So now that we have mu equals t, we can now multiply both sides by this integrating factor and find out that now suddenly our equation is exact. So let's go ahead and do that. So on both sides of the equation, if we multiply through by t, we'll have t times m, and m, we recall, is 3ty plus y squared, plus mu times n. So mu is t, so t times n is t squared plus ty, times y prime, and then equals mu times 0, which is 0. So if you distribute that through, you get 3t squared y plus y squared t, plus t cubed plus t squared y times y prime equals 0. And just to check for exact, if I take the derivative with respect to m sub y, so if I take the derivative of this with respect to y, of 3ty squared plus y squared t, I will get 6ty plus 2ty. And if I take the derivative with respect to t of n, which is t cubed plus t squared y, or am I mixing these up? Nope, little tiny error here. So here I should have had 3t squared, not y squared, just 3t squared y. And the derivative of that with respect to y will just be 3t squared. 3t squared. So now with respect to t, taking the derivative of mu n with respect to t will give me 3t squared, and y is a constant, so this will be derivative of t squared is 2t, y times 2t is 2ty, and you see that we have fixed our problem. So this is where I said we could proceed as we did before. So what we need to do is to find psi now. So what we need to do in order to take care of that is we need to take the integral of this piece, so psi d psi dt, which is what m is. When I take the integral of this, 3t squared y plus y squared t, we want the integral of this with respect to t. That means we're going to take the integral of this with respect to t. So that comes out to, let's see here, the integral of 3t squared, 3y we can factor out. The integral of t squared is 1/3 t cubed. So the 3 and the 1/3 will cancel out, and we'll have t cubed y. The integral of this with respect to t, y squared is a constant. Integral of t is 1/2 t squared. So I have 1/2 y squared t squared. And then of course when you're integrating with respect to t, any function of y may have gone away. So that means psi is equal to this thing. Now also d psi dy we know is equal to the n piece. So we need to look at now t cubed plus t squared y. And that we want to integrate with respect to y to obtain the original psi function. So psi is also equal to, with respect to y, this is a constant. So t cubed times 1, the integral of 1 is y. The integral of this with respect to y, t squared is constant, so integral of y is 1/2 y squared. So this will be 1/2 y squared t squared. And then of course when you integrate with respect to y, any function of t may have gone away. We already see that the pieces match, right? We get a t cubed y there, we get a t cubed y there. We've got a 1/2 t squared y squared there and there. And then we don't have anything else, right? So that means that I could write this as plus 0, and I could write this as plus 0. And so that means there's no standalone functions of y, so I'll equate that to 0. And there's no standalone functions of t in this side, therefore g of t is 0. So it's an identification game. And what I can conclude now is that psi of t comma y is equal to t cubed y plus 1/2 y squared t squared. And the solution of a exact ODE is going to be psi of t comma y equals arbitrary constant. So that means t cubed y plus 1/2 y squared t squared equals constant. And that is my final solution. Now I could, in theory, solve for y by using some quadratic formula stuff, but that's going to get a little tricky. So we shall go ahead and leave it there.